What light actually is? You think you know what light is. You flip a switch, the room gets bright. You open your curtains, sunlight pours in. You see colors, you see shapes, you navigate the world. Light is just there. It's the most obvious thing in the universe, except it isn't. You have absolutely no idea what light is. And the moment you try to pin it down, the moment you ask the simple question, what is light made of? The entire foundations of reality start to crumble beneath your feet. Let's start with what you think you know. You probably learned in school that light is a wave. Maybe your teacher showed you a diagram with wavy lines like ripples on a pond. You nodded. It made sense. Waves travel, light travels. Waves can be bigger or smaller, but light can be brighter or dimmer. The metaphor worked. You moved on with your life. But here's the problem. If light is a wave, what is waving? When you see water waves, you know what's moving. It's water. The water molecules go up and down, and that disturbance propagates across the surface. Sound waves, air molecules compress and expand. The air is the medium. Every wave you've ever experienced in your daily life is a disturbance in some material substance. So, what's waving when light travels through empty space? This question tormented physicists for centuries. They invented something called the luminiferous ether to make themselves feel better. They said, okay, there must be an invisible substance filling all of space, and light is a wave in that substance. Problem solved. Pat ourselves on the back. Go home. Except they couldn't find it. They built incredibly precise experiments to detect the motion of Earth through this ether. If we're moving through it, we should feel a wind, an ether breeze. They looked. Nothing. The ether didn't exist. Light was traveling through nothing, waving in nothing, and yet it was definitely waving. This is your first hint that light is not going to cooperate with your intuition. Light does not care what makes sense to you. Now, before we go any further, I need to destroy another comfortable lie you've been carrying around. You think light is fast. You say the speed of light like it's just a really big number. 186,000 miles per second. Impressive. Fast. But that word fast is deceiving you. It makes you think light is just like a very quick car or a very speedy bullet. Light is not fast. Light is the speed limit of information itself. Nothing can go faster. Not because we haven't built a good enough rocket, not because we need better engineering, but because the universe itself is structured such that light speed is the maximum rate at which cause and effect can propagate. When you say light is fast, you are backwards. Light defines what speed means. Everything else is slow compared to the cosmic speed limit. This has consequences you don't appreciate when you're just flipping light switches. If the sun exploded right now, you wouldn't know for 8 minutes. Not because the information is sluggish, because the universe itself doesn't allow you to know any faster. There is no cosmic telephone line that works instantly. Light speed is the universe telling you. This is how fast now becomes then. But let's get back to the question of what light actually is, because this is where things get truly disturbing. We said light is a wave. Fine. But in the early 1900s, some very annoying experiments started showing up that waves couldn't explain. Here's one. Shine light on a piece of metal. Sometimes electrons pop out. This is called the photoelectric effect. Now, if light is a wave, you'd expect that brighter light, more energy, would knock out more energetic electrons. Makes sense, right? More wave, more power, bigger kick. Wrong. What actually happens is this: the energy of the ejected electrons depends not on how bright the light is, but on the color. Blue light knocks out faster electrons than red light, no matter how dim the blue is or how bright the red is. Brightness determines how many electrons pop out, but color determines how much energy each one has. This makes no sense if light is a smooth, continuous wave. It's like saying a gentle tap from a blue hammer hurts more than a massive swing from a red hammer. The wave picture is broken. Enter Einstein. Not with relativity this time, with something arguably more revolutionary. He said, what if light isn't just a wave? What if light comes in chunks, packets, particles, little bullets of electromagnetic energy? He called them quanta. Later, someone with a better sense of marketing called them photons. Each photon carries a specific amount of energy, and that energy depends on the frequency, the color of the light. Blue photons pack more punch than red photons. When a blue photon hits an electron, it delivers all its energy in one discrete whack. The electron absorbs the whole photon or nothing at all. There's no in between, no half a photon, no gradual wave washing over the electron. It's a transaction. Bang. Done. This is where your brain should start to itch, because now we have a contradiction. Is light a wave or a particle? The answer is yes, and that yes is not me being clever. It's the universe being impossible. Light behaves like a wave when you're not looking at it. It spreads out, it interferes with itself, it bends around corners. But the moment you try to detect it, the moment you try to measure it, it acts like a particle. It hits a detector in one specific spot. It delivers its energy in one discrete chunk. You can't catch half a photon, you can't split it. It's either there or it's not. This is called wave-particle duality, and it's not a poetic metaphor. It's an operational fact. Light is both or neither, or something else entirely, that we don't have words for because our brains evolved to throw rocks at deer, not to understand quantum mechanics. Let me make this even more viscerally disturbing with an experiment you can actually do if you have a few $1,000,000 and a lot of patience. It's called the double slit experiment, and it is the most unsettling thing in all of physics. Take a light source, shine it at a barrier with two narrow slits in it. Behind the barrier, put a screen that lights up when photons hit it. If light is made of particles, you'd expect two bright lines on the screen, one behind each slit. Bullets go through holes. Simple. But that's not what happens. You get a pattern of many bright and dark stripes, an interference pattern. This is what waves do. When two waves overlap, they can add up, making a bright spot or cancel out, making a dark spot. The light is clearly acting like a wave, spreading through both slits and interfering with itself. So, okay, fine. Light is a wave. But wait, now dim the light way down. Send one photon at a time, one single particle of light. It can only go through one slit or the other, right? It can't split in half. It's a particle. You watch the screen. Each photon hits at one spot. Dot. Particle behavior. But if you wait, if you let thousands of these individual photons accumulate, the dots build up into the interference pattern, the same stripe pattern you got with bright light. How? How does one photon going through one slit know about the other slit to create an interference pattern? How does it interfere with itself? Is it going through both slits at once? So you decide to check. You set up detectors at the slits to see which one the photon goes through. And the moment you do that, the interference pattern disappears. Now you just get two lines, particle behavior. The act of observing, of measuring which slit the photon used, changes what the photon does. This is not a measurement error. This is not a technical limitation. This is the universe telling you that light does not have a definite path until you force it to. Light exists in a state of superposition, a ghostly overlap of possibilities, until the moment of detection collapses it into a concrete event. If this makes you uncomfortable, you're in good company. Einstein hated it. He spent the last decades of his life trying to prove that there must be some hidden reality underneath, some deterministic mechanism we're missing. He failed. Every experiment we've done since has confirmed that the universe really is this weird. Light really does behave this way. Now, I know what you're thinking. You're thinking, like, okay, quantum mechanics is strange. I've heard this before, but what does it mean? What's really going on? And here's where I have to tell you something you won't like. It means nothing. Or rather, it means we don't get to ask what's really going on. We only get to ask what we will measure. Physics is not about discovering the hidden gears behind the curtain. It's about predicting what the instruments will say. This is the Feynman approach. Shut up and calculate. Don't ask what the electron is really doing when it's not being observed. That question is meaningless. The electron doesn't have a definite position until you measure it. That's not because you're ignorant of where it is. It's because where it is not a property the electron possesses until the measurement forces it to pick. Light is the same. A photon doesn't have a definite path through the double slits until you measure which slit it went through. Before that, it exists in a superposition of both paths. And this isn't just quantum mysticism. This is what the math says. This is what the experiments confirm. This is reality.